see how it over an algebraically closed field. And then, so we on Severi group, which is the quotient of the divisor class group modulo numerical equivalence. So here we have the involution given by the permutation. Of the factors, and I have an element here, alpha. I will denote by alpha transpose its image under this involution. So the main result that we discussed, which is a theorem of Weil, is a description of this group. So the description was the following. So this neuron Severi group of x times x, I will also refer to this group as correspondences from x to x. So this is isomorphic to z times endomorphism of a group scheme, which is the Picard group, pick 0 of x. And this is endomorphisms in the category of group schemes, right? So maps from this scheme to itself that preserve the group structure, right? Plus times z. So I have alpha here. I will denote its sort of coordinates by alpha 0, alpha 1, and alpha 2. Well, this is not equality. This is an isomorphism, right? So so how this map was constructed? Alpha 0, which is just an integer, is intersection. So I can take a cycle on x times x, and I can intersect it with x with x0 times x, where x0 is any point. This gives me an integer. So this is the, I take a cycle on x times x, and I intersect it with the vertical line. And alpha 2 is intersection of alpha with the horizontal line. And the definition of alpha 1 is more involved. So here is what we did. Yes? So this is construction of the map. How we defined alpha 1? Well, I defined them all at once. So we look at the Picard group of x times x. And so the neuron Severi group is the quotient of the Picard group. Now, what is this group? So if you have a line bundle on x, you can construct a line bundle on x in two different ways. You can pull it back with respect to the first projection or with respect to the second projection. So the map from this to the Picard group of x times x modulo pick x. I will put 0 here. I take degree 0 bundles times pick 0x. So this is a subgroup here, right? Its elements are just tensor products of line bundles pulled back with respect to the first projection and with respect to the second projection. So you have this quotient here, and we identify this quotient with, that was kind of the, using the universal property of the Picard scheme, we identified it with Z times endomorphisms of the group endomorphisms of Jacobian of the peak 0 of this scheme times Z. This is the equality, and it follows. So essentially, well, if you have remember that if you have a line bundle with a trivialization at x0 times x, then it defines a map from x to the Picard scheme by the universal property of the Picard scheme. And we proved that this map extends uniquely to an endomorphism of the Picard scheme. That was the idea. So, okay, now, so this this gives us a map. So we have this map. So degree 0 line bundles, either of these two projections, are in the kernel, right? So because what is a degree 0 line bundle pulled back with respect to, well, what is the pullback of the degree 0 line bundle on X? Its divisor is, well, it's generated. So peak 0 is generated by difference of 2 points, right? This is degree 0 divisors. So when you pull it back, you get 2 lines, one with positive sign, another one with negative sign. And the intersection of this divisor, this is +1 and this is negative, intersection of this divisor with any divisor is 0, because every vertical line, right? Because the intersection, if you have any curve, then the intersection of this curve with this horizontal vertical line and this vertical line is the same. Does it make sense? It's just the degree of the projection of this curve. Steeping. Mm-hmm. Good. So, so this shows that this map from the Picard group of x times x to this guy factors the quotient, and the quotient is isomorphic to this, and therefore we have we get a map. Okay. So the theorem that I didn't give a complete proof of this, but I indicated construction in the inverse direction, is that this map is an isomorphism. That's true. Okay, so what a corollary of this is that this group has a ring structure. This is product of rings. Okay, so this is a non-commutative ring in general, and so I also explained sort of a geometric interpretation of this. Okay, so this gives a ring structure on the neuron severity group. I will refer to it as composition of correspondences. And I gave a more geometric construction of this ring structure. Okay, so if I have two divisors, C and Да. Мы берем группу Пикара, и в ней берем подгруппу, состоящую из дивизоров, которые с любым другим дивизором пересекаются по нулю. Это называется группа нейронной Северия. Фактор называется группа нейронной Северия.
Сейчас, а как еще раз структуру кольца?
Ну, look. So Z is a ring. Да, по координатам. Good. So there was also a geometric description of this product. So what is the geometric description? If you so suppose you want to compose two elements. Well, take the product with respect to this ring structure. Again, I refer to the product as composition. So what is it? So you look at the following diagram here. X goes to take 4 copies of X. So you can take C times D and think of this as a divisor here, all right? So then I want to restrict it to the partial diagonal. So this is a partial diagonal, I, and it's given by the equation that these two coordinates are the same, right? So you simply embed x into x times x as the diagonal. And then you also have the projection to these two factors. And this is pi 1, 3. And what you do, you take a cycle, this cycle here, you pull it back, sort of. You intersect it with this diagonal, and then you take its push forward. Okay? So, good. So, for example, a basic example to have in mind is the following. If you, which is clearer from this definition, is that if you take, if you have two maps, F and G, and you look at its graphs, then the composition with respect to this structure is just gamma of F composed with G. So this explains the notation that I'm using and the terminology. Okay? So, so this is another description of the same ring structure. So what else do we have on this ring? What other structures do we have? Well, we also have the trace, the map that I call the trace map from the Néron-Severi group of x times x to integers. This is map of abelian groups, which takes trace of alpha of a cycle is simply intersection of this cycle with the diagonal, right? So in the case of gamma F, this is just the number of fixed points of my F. And okay, and we also have this involution. This involution has the property that alpha composed with beta transpose is equal to beta transpose alpha transpose. Again, this transposition is given by permutation of factors here. Okay, so then we also have another property is that so if you take the trace of, let me, okay, alpha transpose composed with beta transpose, right? I claim that, so alpha and beta are two cycles on x times x. I claim that this is the same as the intersection of alpha and beta. This is the intersection. So that's, let me explain this point. So how does it work? Okay. So let's look at this geometric definition. So I'm supposed to take two cycles, apply this construction, and then I want to intersect it with the diagonal, right? And compute the number of points in the intersection. So, okay. Let's see what we have. So I claim that by definition, this is equal to the intersection of alpha t times beta. This is a cycle on x times x. So here I take this cycle and I intersect it with the diagonal where the second and the third coordinates are equal. And now I also want to intersect it with the diagonal when the first and the fourth coordinate are equal. So I will write it as follows. So I think of this as a cycle on x times x times x times x, and I intersect it. So this is dimension 2 cycle, and I intersect it with another dimension 2 cycle. Again, this is where the first coordinate is equal to the fourth coordinate, and also the third coordinate is equal to the second coordinate. Yeah? So remember that this alpha t is obtained from alpha by permuting the factors. So, okay, so now I claim that this is the same as. Ну, потому что мы должны сделать? Мы должны вот сначала вот взять вот наш цикл вот здесь. Да. Ага. И потом еще ограничиваем на диагональ. Okay. So, and then this is the same as alpha times beta intersected with a diagonal where I need to, where the first coordinate is equal to the third coordinate and second coordinate is equal to the fourth coordinate. Yeah? So, and this is by definition the same as. Good. So, and last piece of structure that we have here is have a remarkable positivity result. So I will formulate it as follows. So, okay, so for every alpha in here, and endomorphisms of this middle term, p car of x, and this is a subgroup of the Néron-Severi group, trace of alpha transpose alpha is greater than 0 for every alpha not equal to 0. So why that? So this is by the formula that we just proved. This is self-intersection of the cycle on x times x. And this intersection, this alpha, sits here. So it's orthogonal to the vertical line. It has trivial self-intersection, is intersection with the vertical line and also with the horizontal line. And therefore, it has trivial intersection with this divisor. And this divisor on x times x is ample. So this is the Hodge index theorem. Whenever you have a cycle on x times x, whose intersection with an ample divisor is 0, its self-intersection is negative. Right? This is the Hodge index theorem. Index, yes, theorem. So what is the Hodge index theorem? It's the following assertion. Suppose you have a surface and an ample line bundle, ample divisor. Suppose you have any cycle, alpha, on your surface, whose intersection with an ample divisor is 0. And its self-intersection is negative. And that's a corollary of this fact. Because if alpha sits in this part of the Néron-Severi group, it means that its intersection both with this line is 0, right? So how we define this projection, alpha 0 and alpha 2? Вот крест, да. Потому что этот крест, вообще, если у вас есть два многообразия, вы берете обильный дивизор на одном многообразии, обильный на другом. То есть внешнее тензорное произведение будет обильным дивизорным произведением. Вот что вот этот крест? Это pullback с точки. Дивизора точки. Вот.
Это два pullbacks.
Да, прости, тензорное произведение двух pullback'ов. Но, значит, каждый из этих pullback'ов, каждый из этих линейных расслоений на кривой, оно обильно. Поэтому внешнее тензорное произведение тоже. Very good. So we have this picture, and now, as I promised, I want to tie the ends. So let me explain. Let's look how this picture looks like over the field of complex numbers. Then everything can be described very explicitly in terms of elementary linear algebra. This is, in a way, a motivation for this. Though the results, this formulation makes sense over any field. This is the advantage. It's very, very simple over the field of complex numbers. So remark, it will be a long remark. So let's look at the case when k is c. So then I have the following theorem. So let's look at the Picard group of x times x. So from the Picard group, I have the Chern class map, the map that assigns to every divisor in my class, or every line bundle its first Chern class, to H2 of x times x with integer coefficients, right? This is the Chern class map, C1. You can define it, for example, using the exponential long exact sequence, exponential short exact sequence. Z goes to O goes to O star. This is exponential. And the connecting homomorphism from first homology of O star to, this is analytic topology, the map from the connecting homomorphism is this. Okay? So using the Coinage formula and the Poincare duality, we identified it with комплексная кривая. Проективная кривая над полем комплексных чисел. Гладкая проективная кривая. Ну, оно алгебраическое, на нем по любому алгебраическому многообразию над полем комплексных чисел можно построить аналитическое. Но экспоненциальная последовательность, она имеется только в аналитической топологии. Very good. So this is the Betti homology, right? That's we view X times X as a topological space with classical topology. So, and this group is isomorphic to endomorphisms of H0 XZ times endomorphisms of H1 XZ times endomorphisms of H2 XZ. Right? That was the, again, I explained this last time. It's straightforward. You just use the Q-net decomposition together with Poincare duality on X. Does it make sense? So this group is Z, of course. This group is also Z. Well, this group is also Z. Сумму я пишу как произведение. Для абелиогрупп это одно и то же, но поскольку меня интересуют кольца, то как-то сумма колец это не хорошая штука. Ну, в общем, это прямая сумма групп. Хорошо? Понятно. Good. So this is Z. This is Z. Having compared it with the formula that I still have here. So this is something. So the theorem first describes the image of this map. Right? And secondly, well, there are two assertions here. So first I will describe the image. Who knows the description of the image? Dima. So you attended the course by Verbitsky.
So these are the Hodge cycles.
Hodge cycles. How to describe them in terms of this factorization? So, well, if you believe in this theorem, so, well, it is easy that this map is surjective on these two components, right? If you just take the vertical line or horizontal line, it gives you precisely these two copies. So the question is, what is the image here? So inside, so this is just a free abelian group of rank 2G. So this is a matrix algebra over integers. And I want to describe the image of this Chern class there. So what are the algebraic cycles here? So think for a second of a basic example of a cycle, a graph of a map. So if you take a map from X to X, then under this composition, it just goes to the induced map on homology. Every map F from X to X, on the one hand, it gives you a cycle, the graph of F. On the other hand, it gives you an endomorphism of H0, H1, and H2. So what are the properties of this endomorphism? Very good. This is symplectic. Though being symplectic is not an additive condition. So, ну, да, здесь на H1 есть спаривание Панкара. The symplectic structure is, by the way, that's a very good point. So I claim this is a topological statement, that this operation transposition here, right, on cycles, here we have the permutation. It goes to the adjoint operator with respect to the Poincare pairing, right? So you have endomorphism of a vector space which is equipped with a skew-symmetric Poincare pairing. So if you have an endomorphism of a vector space, you can take its dual, or adjoint operator, right? That's what transpose stands for. But so this, in the case when you start with a map from X to X as it was observed, so this the corresponding endomorphism preserves the symplectic structure up to a constant. This constant is the degree. But again, not an additive condition. So it cannot be true for the entire image because sum of two symplectic matrices is not symplectic. So I want an additive condition here. So if you have a map from X to X algebraic map, of course it gives you a map from this group to itself, but it preserves the Hodge structure. Right? Remember the most important, so you have H1 of X tensor with Z coefficients, and if you tensor it with complex numbers, this becomes isomorphic to the de Rham homology of X, and this complex vector space comes together with a filtration given by just global forms on X. Right? Global one forms. So every map, holomorphic map, from X to X, preserves this subspace. So the answer is that now what should be the answer? Because it preserves pullback of any holomorphic. One form is again holomorphic, right? So every map from X to X induces an endomorphism of this lattice, and it also preserves this F1. So what what would be the reasonable conjecture now? What should be the image of this cycle class map? The answer is that you just take all endomorphisms of H1 of X, view it as a Hodge structure. So what does it mean? So this is endomorphism in the category, in the category of Hodge structures. So a Hodge structure in this case consists of a lattice together with a filtration on its complexification. So you look at all endomorphisms of this guy that take F1 to F1. So and then you also have Z. Нет, совершенно не то же самое. Симплектические — это, еще раз, сумма симплектических, не симплектическая.
А это эндоморфизм происходит решетку?
Да, да. И решетку, и фильтрацию. Вот я утверждаю, что если for a general Hodge structure, generic Hodge structure, there are no endomorphisms at all, except for multiplication by integer. Because if this is kind of, this filtration is generic, right, in general position, then there are no matrices with integer coefficients that would preserve F1. Значит, so this is the theorem, and now I am ready to state it. So the theorem asserts that this map factors through the Néron-Severi group of x times x, and it induces an isomorphism. So first of all, this Chern class map factors through the Néron-Severi group, and it induces this isomorphism. Okay? So, and the second, and this is of course, this another part of this theorem is that this is Z times endomorphism of the group endomorphism of the Picard P0. Okay? So, let me explain the proof of this. So, again, in the complex situation, everything can be described just in terms of this very simple linear algebra structure. Questions? And this is a way to formulate it abstractly over any field. And we are going to see in a second that even this positivity result, the Hodge index theorem, is an immediate corollary of that decomposition. So, maybe I should say that, so under this map, trace of alpha is, right? So this self-intersection with the diagonal is equal to the alternated sum, sum I equal to 0, 2, there are two terms, negative 1 to the I, trace of alpha I acting on homology. This is a topological statement. We discussed it also last time. And, transposition corresponds to the adjoint with respect to transpose correspondence correspond to the adjoint linear map with respect to the Poincare pairing. Good. So the proof, well, the first assertion, so there are two assertions that you have a surjective map that it factors through, well, it's the first assertion. Let's start with this one. Да? Yeah, that's a part of the theorem that I will explain in a second. Okay? Nothing of this is, there are many parts. So, proof. So let's give a name to x times x. This is y. And now there is what's called the Hodge fundamental theorem in complex algebraic geometry. I will explain its proof. Hodge 1-1 theorem. And it describes the the Picard group of Y, right? Y is x times x, and you have this Chern class map to H2 of Y with integer coefficients. So the Hodge index theorem describes the image of this map. So it asserts that the image lies in H11 part of this, right, with respect to the Hodge decomposition on Y. And it's surjective. So there is something, the most famous conjecture probably in quantum algebraic geometry, the Hodge conjecture, right? It's a generalization of this fact for cycles of higher codimension. And this is the only known case of the Hodge conjecture, which is still very powerful. Нет, для фундаментальных классов. То есть, если у нас есть, например, цикл коразмерности 2, то ему можно сопоставить фундаментальный класс. Он лежит в четвертых когомологиях с целыми коэффициентами.
Сейчас, цикл с элемент Пикара.
Нет, просто цикл — это подмногообразие. Неприводимое подмногообразие. Точнее, прости, пожалуйста, это элемент свободной абелевой группы, порожденный классами, порожденный неприводимыми подмногообразиями. Здесь это коразмерности 1, а там коразмерности 2. Не классы Черна, а фундаментальные классы. Если у меня есть подмногообразие, то у него всегда есть фундаментальный класс в когомологиях. И он лежит, если у меня есть подмногообразие комплексной коразмерности 2, его фундаментальный класс лежит в четвертых когомологиях. Ну, вообще, если коразмерности d, то в когомологиях с номером 2d. Хорошо? И гипотеза Ходжа, она говорит о том, чему равен образ. Вот какие классы здесь представлены алгебраическими циклами. Необходимое условие, чтобы образ попал в H, в такую среднюю часть, когда вот эти два индекса совпадают. Но утверждается, гипотеза Ходжа говорит, что с рациональными коэффициентами, если я возьму циклы с рациональными коэффициентами, это отображение будет суръективным. Вот. А здесь с целыми коэффициентами. Верно, значит, proof, indeed. So the proof is, in fact, one line, but still it's highly non-trivial. So what you do, you just look at gain in the exponential exact sequence. And so you want to describe map x. So how does it work? It works as so you have O star. This is the Picard group. Picard group. Everything is analytic. Then you have H2 of Y with Z coefficients. This is our Chern class map. And so I want to understand the image. In order to understand the image, you look at the next term of this long exact sequence, homology exact sequence. So the next term will be H2 of Y with coefficients in O. Right? So what is this map? Well, in order to understand this map, we need to look at this map. So this map is given by the inclusion. So here we have homology is classical. In classical topology, homology, well, this is Betti homology, or equivalently, this is homology of the constant chief, Z. And this is homology of analytic functions. Z maps to analytic functions because a constant function is analytic. So so what we want to show is that if by this one exact sequence, we know that the image of this map is precisely the kernel of this map. So let's look at this map in terms of the de Rham homology. So I can first map this to de Rham homology, of Y. So how I want to think of the de Rham homology? This is second de Rham homology. Well, one way of thinking of de Rham homology is that it's R2 gamma of the following complex. I take analytic de Rham complex. Right? So a constant function is not only analytic, it's killed by the differential. So this Z maps to this complex because it's, D of Z is 0. So that means that this map here factors, so you have this map which is induced also by a map of complexes. So you take this complex and you project it to its first term. It's a map of complexes. So I decompose the map from Z to O into a composition of two maps, from Z to this complex and from this complex back to O. So So this map, by the Hodge theorem, it's surjective, and the space can be identified with de Rham homology of Y modulo F1. Right? So F1 is defined as homology of this subcomplex, where you put 0 here. So the Hodge theorem asserts only the part that I'm using here is the degeneration of the Hodge spectral sequence. And the Hodge spectral sequence is associated to the stupid filtration of this complex. And this is what Dima proved for us last time. Well, not last time, the end of the last year. Okay? So, using the reduction to characteristic P, by the way. So, and that's the end of the proof. So, we see that this map can be written as the composition of the two maps. First, you map to the de Rham homology, and second, you project to F1. So that means that if you have a class here that lives in F1, then it belongs to the image. H1 term, right? This is one way of phrasing it is F1 intersected with F1 bar. So in particular, it lives in F1. So it goes to 0 under this map. And therefore, it lives in the image. This is a proof of Hodge theory. So now, the next assertion that I need is that C1, so this is kind of the first part of the proof. Oh, okay. Yeah, so I haven't yet finished. So we described the image of the Picard group here as classes that are both integral and live in F1. So now this is a exercise to show that this translates into this description by the Hodge, by the Kunit formula and Poincare duality. So you have a class here. You write it as endomorphism of the homology groups. And now you have to understand what does it mean that the class that you started with here leaves an F1, right? So this is an isomorphism. And here we have F1. Well, we have H2 intersected. I will not write it down. You have, because I have already it here. So you have this subgroup here. And so this subgroup sort of depends on the Hodge filtration, right? It depends on the Hodge filtration in Y. How the Hodge filtration in Y looks like? Y is X times X. So you can use the Kunit formula, and the Kunit formula is compatible with the Hodge filtration. So basically you have the same ingredients. So here you have F1 term. So it's kind of, it is expected that the image of 1 classes here should be described as in terms of the composition here as the subgroup, subgroup here which compatible in a way with the Hodge filtration, right? So the claim is that the compatibility is very simple. You just preserve the Hodge filtration. So, and this is formal. All you need to know are two things. First, that the Hodge filtration, that the Kunit's decomposition is compatible with the Hodge filtration. And secondly, you need to know how the Poincare duality behaves with respect to the Hodge filtration. So, what are this? What is this assertion? So you have H1 of X H1 of X times with C coefficients tensored with H1 of X with C coefficients. And here you have the Poincare map with an H2 of X with C coefficients. And this is C. But it also has a Hodge structure, but this must be trivial. It's just HH1. So the assertion is that this map is compatible with the Hodge decomposition. Right? So write this as H1 0 plus H01, and also here. So what does it mean that it's compatible with the Hodge decomposition? It means that if you take the pairing of this guy with itself, you get 0. This is obvious because if you multiply two holomorphic one forms on curves, you get 0. The same is true here for anti-holomorphic. So, and that's what it means that it's compatible. And right, the only assertion is that the pairing is 0 here and here. These are anisotropic subspaces. Isotropic subspaces, sorry. Good. So that's why you have, this is how H11 appears in this picture. So, so this implies that image that Picard group of X times X maps to endomorphisms of the Hodge structure. right? Oh, I shouldn't write C here. Does it make sense? So star means that I take graded endomorphism, but it amounts really to 18. Good. So this is surject. This means that it lives here. Endomorphism of H star X Z. So the different class map factors through this, and this is surjective. Good. So this is essentially Hodge 1-1 theorem. Now, what else do I have to show? I have to show that this map factors, this Chern class map factors through the Néron-Severi group. This seems to be very hard because you need to show that if a class, intersection of a class, of a divisor with any divisor is 0, then its fundamental class is 0, right? It seems that in order to prove this, you need to construct many divisors, right? How do this condition that intersection with any divisor is 0 seems to be very, very, very complicated because you don't know how many divisors you have, right? So, this should be compared with another, with a Poincaré theorem, which asserts that if you have a class here whose cup product with any other degree 2 class is 0, then the class itself is 0, that the Poincaré pairing is non-degenerate. But here we take the cup product with any class in H22, not only algebraic ones, right? So, but fortunately, in this case, the statement is easy because of the positivity. So, so remember we discussed a week ago. We discussed how the positivity property of the Poincaré pairing here, right? So, so let's see how I want to phrase it. Hodge index theorem implies that if you have a class alpha in H2 of X with Z coefficients, and it's orthogonal to the class of an ample line bundle No, I will just write omega class of an ample line bundle. Right? So if this is 0, then it implies that alpha is non-negative. Yeah? So, so in particular, so you can take for omega just the omega is a class of an ample line bundle. So it's an algebraic class. It's a divisor. And if you know that alpha intersects with this divisor trivially, and it's non-zero element here, then its self-intersection is negative. but alpha is, well, alpha is, so applying this to our algebraic, well, a class here, which is numerically equivalent to 0, you see immediately that its image must be 0. So it shows that it factors. Good. So essentially, what we proved from this is that we have a class here, any class, whose image, whose Chern class is non-zero, then either this number is non-zero or this number is non-zero. Ну, это пересечение, если угодно, вот с таким крестом. Почему? Нет, омега — это фундаментальный класс, да. Это в качестве O от единицы обильного рассвоения можно просто взять вот такой дивизор. Да, да. Окей. Да.
Я не очень поняла. Вот мы поняли, что либо пересечение альфа с омега равно нулю,
либо просто...
в смысле, либо альфа с омега не равно нулю, либо альфа с альфа не равно нулю.
Да, да.
А как это получается, что реализуется по...
Ну как? Ну, допустим, что у нас есть дивизор здесь, который вот тут перешел не в ноль. То есть вот это вот его вот альфа, это вот не равняется нулю.
Да, и мы хотим найти...
Да. Мы хотим найти алгебраический цикл,
хорошо, да.
но вот этот алгебраический цикл либо будет... да, да, да. Good. So now, this implies, so we have surjectivity here, we have surjectivity here. The injectivity part is obvious because the intersection here corresponds to the cup product here, right? So if you know that an element here goes under this Chern class map, in particular that its intersection with any class in H2 is 0, and in particular it means that its intersection with any divisor is 0. So this means that it's isomorphism. Okay? Сурьекция — это была теорема Ходжа, вот эта вот теорема. Вот мы доказали. Почему? Потому что вот просто вот здесь это отображение сурьективно. Я объяснил, что значит, мы доказали... Сейчас, давайте еще раз посмотрим на эту картинку. Вот мы выяснили, что вот это отображение сурьективно. Вот это отображение сурьективно. А вот эта группа, которая здесь написана, она просто по формуле Кюнита равняется вот этой. Ага. Вот так. So this is H2 Y Z intersected with H11. Okay, so here is the theorem, and let me explain. So what we already proved? We proved everything except for this isomorphism here. So I want to identify endomorphism of this Hodge structure with endomorphism of the Picard peak 0. And this is easy. Because, well, Picard schemes is very complicated. But in complex geometry, you have Picard scheme is a group, and in complex it's an abelian group, and in complex geometry you have the exponential map. from the Lie algebra to the group, which is a holomorphic map, not algebraic one. And if your group is abelian, then the exponential map is a group homomorphism, right? And it shows that the Picard scheme is a quotient of the vector space. Not C. Still not, да, это все not C. Okay, so let's first of all let's compute the Picard scheme, Picard group of X, right? So what is a Picard group of? Of X. So I'm interested in the Picard scheme here, but let's first consider this as a set, not really as a set. So again, if you look at this sequence here, right, this exponential sequence, so the peak 0 is, so what are the terms here? This is H1 of, maybe I should. Okay, so you have H1 of X or star. This is mapped to H2 of X with Z coefficients. This is the degree map. We are in the case of curves. The term to the left is, next to the left is XO. And this guy is H1 of X with integer coefficients. So, this will be H0 of X or star and H of XO, right? So we don't have global functions on a compact manifold, analytic manifold. So this is just C, this is C star. And this map is surjective, it's exponential map. So that means that this map is injective. That means that the kernel of this map is simply H1 of X with, of this space, modulo a lattice. So if you have a curve of genus G, then this is a complex vector space of dimension G. And this is, this is a lattice of dimension of rank 2G. Okay? So we identified this group with a quotient. Now this has an analytic structure. This is a vector space, this is a discrete subgroup. So we can think of, it's an analytic manifold. So I claim that the following is true. So if you take the Picard scheme of X and view it as an analytic space, right? This is an algebraic scheme. But every algebraic scheme over C gives rise to an analytic manifold, holomorphic manifold, and I claim that it's isomorphic that this isomorphism is analytic. Okay, I hope that it's clear what the content is. So we just identified sets, but my claim is that this identification is holomorphic. So sketch of the argument here is the following. So this is a group, abelian group. So let's take the exponential map from the Lie algebra to the group. So what is the Lie algebra? Well, the Lie algebra of this analytic group is the same as the Lie algebra of the algebraic scheme, right? And we know what the tangent space to the Picard scheme is H1 with coefficients in the structure sheaf. Using the fact that if you have a coherent sheaf on a projective algebraic manifold, then its analytic homology is the same as its algebraic homology. This is a non-trivial but very general fact for all result of SER. So therefore, we get a map homomorphism from a vector space to this scheme. Right? So this vector space appears here. So, so that means that this is a quotient of this guy by a lattice. And we already constructed an identification between sets. Это сурекция. Если у меня есть гомоморфизм групп, он дифференциал экспонента в единице равен единице, тождественный, поэтому он образ открыт. А это связанная группа. Поэтому это сурекция. So that identifies this with a quotient of this bilattice. And on the other hand, we have this identification, so it remains to check that somehow that this map, this exponential map, is the same as the map from here to here we constructed using this exponential sequence, right? Once we have this, well, we are done. Okay? So, okay, so I think my time is over, but the theorem is proven. And I think I will take another 20 minutes next time, tomorrow, to tie the last end, and then we will move to construction of the Italian homology. It's a group? Потому что есть тензорное произведение рассвоений. Потому что она происходит аналитификацией групповой схемы. Okay?